Welcome everyone. You are joining us for Introduction to Imaging, Radiometry and FLIR Research Studio. This webinar is presented by Teledyne FLIR and hosted by us at Photonics Media. Today, you'll hear from Matthew Hastie, the Global Senior Product Manager for FLIR's Research, Development and Automation segments. Matthew holds a bachelor's in Industrial and Systems Engineering and a master's in International Business. He's joined by Ross Overstreet, who has been with FLIR's science team for 19 years, specializing in military test range and national laboratory applications. Matthew will uncover the basics of infrared technology, explore different sensor types, and teach about radiometric calibration. Plus, Matthew will show how FLIR Research Studio software can revolutionize efficiency and spark scientific breakthroughs for global teams. Before we begin, feel free to ask questions or leave comments in the chat box at any time. If you experience any technical problems during the event, please log out and rejoin. After the webinar, you'll be able to access the recording online, and a link will be sent to your email. So with nothing further from me, I would like to welcome Matthew Hastie and Ross Overstreet.
There we go. I have control now. Hello, everyone. Welcome again to today's webinar. Thank you so much, Haley, for the introduction. And this webinar in general is going to be a brief introduction to imaging radiometry, detector technologies, temperature calibrations, and the incredible tool FLIR Research Studio. My name is Matthew Hastie. I'm the Senior Global Product Manager for the R&D Science and Automation markets, as Haley said. And I'm really excited to be here with you today to get to discuss these topics. And then once again, we have Ross Overstreet with us, who is really a global expert in the R&D and science market for FLIR. Been with us a really, really long time. And before we fully jump in, I just want to say again about the questions. Please submit them in the webinar portal. The reason Ross is here is so that he can answer the questions real time via the question or chat portal. And so if you submit your question, you have a chance to, during the webinar, get some live interaction and get to maybe learn a little bit deeper. And then, of course, at the end of the webinar, time permitting, we will answer as many questions as we can live. And if we don't get to a question, we'll make sure to follow up and make sure everyone's questions gets answered fully after the webinar. So Ross and I are actually going to turn off our videos for the rest of the presentation. We'll come back on with video at the end, but we just want to make sure and save bandwidth so the presentation and audio works as best as possible. So I'd like to start out with just a brief definition that's going to lay the foundation for most of our conversation today, and that's that infrared imaging radiometry is the science of using an infrared camera to measure the amount of IR radiation emitted by objects in a scene. So every pixel in the image formed by a radiometrically calibrated camera carries quantitative information. Radiometric images are more than just pictures or videos. They're actually two-dimensional grids of measurements of the infrared radiation or the temperature imaged onto the sensor from the scene. So let's remember that definition, as that's going to be important throughout today's webinar and really have a baseline for what we're going to talk about. So looking at where we're going during the webinar, here's a brief agenda. At first, we're going to go over an introduction to IR detectors, the basic technology and differences in detector types. We'll then do an introduction to imaging radiometry and what it actually means to have a calibrated camera. And then finally, we want to show you FLIR Research Studio and how it works the way you work, and it'll enable global research teams towards groundbreaking discoveries and new technologies. Keep in mind, this is meant to be a very broad overview of each topic. So there's some topics we're just going to mention, and there's others we'll dig really deep into with some very technical terminology, actually. We could spend hours digging into each one of these topics if we had the time, and our experienced sales team would be happy to follow up with you if needed and dig into any specific topic for an extended period of time. Before we fully jump in, I'd like to tell you a little bit about FLIR and about Teledyne. As many of you know, FLIR is a part of Teledyne Technologies, and Teledyne has many different companies and vast technologies as a part of the team. It's really quite exciting. Teledyne products really are, as you see in the slide, everywhere you look. Our sensors, our hardware, our full solutions, and our software are implemented all over the world in daily life. And they really enable technologies to sense, transmit, and analyze information. But maybe this slide will help give you a little more context. Teledyne Technologies has 4 reporting segments: instrumentation, digital imaging, and that's where Teledyne FLIR is a part of, aerospace and defense, and engineered systems. Within each of these companies, you may recognize, within each of these segments, you may recognize a few companies, such as Teledyne DALSA, Teledyne Brown Engineering, Teledyne LaCroix, Teledyne Princeton Instruments, Teledyne Judson, and many more, and of course, Teledyne FLIR. And just from the list of technologies here and companies, you can see the vast technical expertise and the wide reach of Teledyne. And finally, we say this a lot, we're really proud that we have the full spectrum of imaging technologies at Teledyne. We're uniquely positioned with products spanning from X-ray through infrared and out to radio waves. Also, our products range from deep sea to deep space products and really everything in between. See, we're proud of that tagline, all wavelengths, all applications, from deep sea to deep space. And FLIR fits very nicely into this portfolio with our strong reputation for infrared sensor technology, for infrared cameras, and full solutions based around infrared. As many of you know, FLIR is the global powerhouse in commercialized infrared technology. So we talked about the company a little bit, so let's switch gears and start to dig in to more specifically infrared. See, our cameras typically operate in the infrared spectrum, located at wavelengths longer than the visible spectrum that most of us are used to seeing with our own eyes. Sometimes we call this infrared spectrum the sixth sense. For a moment, let's just talk a little bit about infrared energy and how it relates to visible light. For most of you, this might have been covered in a physics course, but I'd like to level set just to make sure we're on the same page. The graphic at the bottom of the slide shows a section of the electromagnetic spectrum, which illustrates how infrared or thermal radiation relates to other forms of electromagnetic radiation. So on this graphic, you can see, or maybe be reminded that the wavelengths of infrared radiation, once again, are longer than visible wavelengths that our eyes see and are tuned to see, yet they're shorter than microwave and radio wavelengths. But like visible light, infrared radiation travels through space at the speed of light. So it can be focused, it can be reflected and refracted, just like visible light. You just need special materials to be able to do this. In addition, the infrared band is actually broken up into a number of subbands. You can see these subbands displayed above the overall electromagnetic spectrum on this slide, and we'll go over them real quick. The first is the NIR that you'll see on the far left, or the near infrared band. That's just beyond visible and covers from about 700 nanometers to around 1.4 microns. The light in this region is not due to thermal radiation, and many CCD and CMOS detectors have sensitivity in this band. This is the band that's most often used in non-thermal night vision devices. The next one is SWIR, or SWIR, also standing for shortwave infrared. This spans from 1.4 to 3 microns, or maybe 0.7 to 2 microns. It's a region dominated by reflections and absorption. Typical detector materials here could be InGaAs or Indian gallium arsenide. Also, there's colloidal quantum dot, there's SLS, INSBE, and MCT that can run in some of these bands here. And although it's still not classically a thermal band, SWIR cameras can be calibrated for high temperatures starting around 400 degrees Celsius, since that's about the point where thermal emissions overtake the signal created by reflections. SWIR is good for seeing through materials like glass. It's also useful for visibility through haze, capturing SWIR spectral information, seeing through layers of paint with non-destructive evaluation techniques. I'd also like to point out that FLIR SWIR camera is so linear in response that we can calibrate it for thermography applications starting around 400C, like I mentioned above. And so what I mean by that is calibrated per pixel for temperature. I'd also like to say before we move to the next, which is MWIR, that I'm giving bands for each of these subbands, but they can vary depending on how you define them and the material. So you may say shortwave, you've heard it be a little bit different band, or midwave, and that's okay. These are just general definitions of the range of each band. And the next one, MWIR, or midwave infrared, is the region most common with cooled cameras. It's typically between 3 and 5 microns, but there's also broadband midwave, which is typically 1 to 5 or 1.5 to 5 microns. And this is where the thermal infrared band starts in materials like indium antimonide, and then also MCT, or mercury cadmium telluride, it's always a hard one for me to say, are most often used as detector materials. Recently, there's also been development in hot midwave options, such as strain layer superlattice materials, which in the past were just long wave options. The slope of Planck's curve here enables excellent contrast. The detectors are exceptionally sensitive at typically better than 20 millikelvin NEDT, and for many applications, there's enough energy to adequately fill detector wells to run very high frame rates in the midwave. Finally, long wave infrared, or LWIR, you'll see that on the far right, starts around 8 microns and covers out to about 14 microns. This is the thermal band covered by most low-cost and entry-level infrared cameras, since they often use thermal resistive detectors like microbolometers. We'll talk more about that in a minute. You'll see this technology in many handheld cameras. Higher-end infrared cameras also can run in this band, and they use cooled detectors made from strain layer superlattice or SLS material. You'll also see MCT in this band. SLS long wave has benefits including broader thermal ranges, short integration times, and for those interested in spectral measurements, it has long wave response. In addition, in the long wave, you can experience fewer solar artifacts, and it's typically better for cold temperature measurements. At the end of the day, all of these wavebands have unique capabilities found at each range of the spectrum, and it's really best to talk to a FLIR science sales engineer to understand the trade-offs in your specific application. So I know that was a lot of information there, so I want to show it in just a different format to maybe help cement in the different detector types and wavebands in the infrared. So this slide gives a little bit different view of the different detector technologies. There's a lot of technologies listed here that you heard me mention in the previous slide. And initially it might be confusing, but there's really two types of detectors here. You'll see towards the right in the bottom, it's the orange and red colored. It's called the microbolometer or bolometer. You'll see it right there. These are commonly referred to as UBOLOs or even thermal or power detectors. And they operate in the long wave infrared region and are the detectors used in most common and low cost infrared cameras like mentioned before. We'll talk more about how these detectors work in the next couple slides. So the second type are photon counting detectors or cooled detectors, and they're made from a variety of different materials. All of the other detectors on this slide are photon counting, and they cover all kinds of different wave bands, as we mentioned previously, and as you can see here. We recognize there's other detector materials out in the market currently, and we're also aware there's new materials being developed each year. But these are the most common materials you'll see specified in commercial off-the-shelf infrared cameras, and are the materials FLIR has a history of using or looking at in recent years. And so this can be complicated looking at slides, but as long as you understand these two types, thermal or power detectors and photon detectors, it helps summarize this. So let's dig into the two types of detectors here. The microbolometer category of detectors I mentioned on the previous slide is a type of thermal detector. So what exactly does that mean? Well, it means it produces a resistance change when it's heated. So an infrared camera typically has a focal plane array containing several thousands of detector elements, with each element being a single bolometer. With the lens of the camera, we focus the infrared radiation coming from the target onto the detector elements. And as the radiation strikes each of these elements, they heat up and their respective resistance changes. We run a constant current across the sensor, and so then we can measure the change in voltage due to the change in resistance. And then we use a readout integrated circuit to measure the voltage change for each element and convert the reading to a digital count. This digital count or digitized data for each pixel element is then calibrated to temperature, assigned a color or grayscale value, and presented as an infrared image that many of us are used to seeing. At this point, the user has temperature per pixel and an image representing thermal patterns across the scene. It's really quite powerful, the data that the user has at this point. The material of the microbolometer has a certain amount of thermal heat capacity, which along with thermal conductance limits the response time of the detector. This response time is referred to as the thermal time constant, and it's the time parameter that expresses how quickly a microbolometer can react to incoming thermal energy. It's intrinsic characteristics of microbolometers, and it can't be changed or adjusted by a camera user. Most bolometers today have thermal time constants between 7 and 16 milliseconds. The materials you're most often going to hear referenced when we talk about infrared cameras with microbolometer detectors are vanadium oxide and amorphous silicon. And the great things about these type of detectors and materials is they don't require cooling in order to operate effectively or without significant noise. So this is why you'll hear cameras that use microbolometer detectors often referred to as uncooled cameras. A final view of bolometers is the fact that they entail a rolling shutter. This is really a pretty incredible slide here. What you see is the detector from a FLIR T1020 HD handheld camera that we are looking at. We used one of our cryo-cooled strain layer superlattice long wave cameras to capture this data, since it can see through the same long wave friendly window that's on the handheld camera, and we can actually record the detector in action to let you see this rolling shutter. So as you can see here, bolometers read out row by row. It doesn't take an impressive demonstration to consider how that type of readout is going to cause problems if you have a high-speed event you're trying to capture. When you read out row by row, the detector actually provides the time required for the pixels to return to thermal equilibrium. So you might ask, well, what's the integration time for a microbolometer in order to evaluate if it's going to work on your application or for your speed requirement? Well, bolometers don't technically have integration times. The equivalent is what we mentioned on the last slide, and that's the time constant. We can't ignore thermal time constants because they're intrinsic to the design of the microbolometer. And when considering a fast event, a good rule of thumb is to ensure that the event is slower or longer than 60 milliseconds. This is to ensure that you have the time to read the charge and have the time for the detector to return to thermal equilibrium to accurately capture the next frame. Again, if you don't allow enough time to pass, residual charge will carry over to the next frame, resulting in blurring or thermal smear. We'll show this in a few slides, actually. I'll also add a caveat here that while this is a decent rule of thumb, it's not a hard and fast rule, and it can be very detector and application dependent. It's also very important to note that this 60 millisecond time frame is for a single thermal event. If you have a dynamic scene where the temperature is going up and down and changing quite a bit, you'll need to evaluate whether the changes are slow enough for the detector to keep up and maintain accurate readings. Thermal time constants are clearly the challenge for microbolometers, right? When it comes to going faster. So you might ask the question, why hasn't this been addressed? Well, the response of the detector is directly related to thermal resistance. And any efforts to decrease that resistance, you could thin the detector element, you could decrease the size, will actually have a directly proportional effect on the sensitivity, which would bring it to an unacceptable level. So, needless to say, this is not trivial, and it's a challenge for the entire industry, and this is where bolometers are actually at today. The second category of detectors are actually called photon detectors. These types of detectors collect photons of light or other electromagnetic radiation emitted from a source and convert them into electrons through what we call electron hole pairing. The electrons are collected and stored in an integration capacitor for a certain time period. This time period is known as the integration time, and it's similar to an exposure time of a visible camera. At the end of the integration time, the circuit is then shorted, and the charge is read out by a readout integrated circuit. The ROIC, or readout integrated circuit for short, converts the electrical signal to a digital count, which then is calibrated for temperature against a known reference or presented as a raw image. Photon counting cameras are very flexible and precise in their operation, since integration time can be adjusted to account for the amount of inbound photons from the target of interest. The available integration times on photon counting detectors can range from minutes to microseconds. So, since integration time, integration capacitors, well fill, all can be difficult concepts for those of us without electrical engineering backgrounds, I want to show you the buckets in the rain analogy. Some of you may have seen this before, but it really helps to understand how integration time works. At the bottom, you'll see examples of an integration capacitor, 2 buckets. These represent a pixel, so you can imagine an array of these buckets matching a typical detector resolution, say 640 by 512 buckets. In this analogy, the rain represents the photons produced by the scene. So in a cold scene on the left, 20C, you'll see there's fewer photons will be produced, filling the bucket at a slower rate. But in a hot scene on the right, 400C, many photons are produced. So on the left, we have a light sprinkle, and on the right, we have a heavy thunderstorm, which means the bucket is filled more rapidly when the temperature is higher. So when we read the detector, we would take the amount of rain photons collected at that point and produce our image. So the next term here is well fill. Well fill is a term you'll see on cooled detector spec sheets, and it just refers to how much energy the capacitor can collect, or in this example, the size of the bucket. Think of it as the depth of the given detector unit cell. It can also be used as an active percent amount of fill, like when you're calculating any DT and how we're using it in this rain example. So a shallow well fill will fill rapidly in many instances, where a deeper well is going to take longer to fill. A very simple way of looking at it is the fuller the well at the time of integration, the more energy that's been collected, and the better the imagery is going to be. The integration time is simply how long we leave the bucket or the well open to be filled by the rain or the photons. So, in summary, let's go back to the cold scene above. A longer integration time would be needed to attain a high enough well fill for imagery. This would inherently begin limiting the speed at which you're going to be able to capture versus the hot scene, where the target well fill is reaching much faster, enabling faster frame rates. Compared to a bolometer, the integration times can be drastically shorter at 300 nanoseconds or less, though the recommended minimum is typically 10 microseconds or so for the best performance and most accurate data. So I hope you see by this slide and this analogy that the integration time and the energy in the scene is a key driver in the ability to run cameras at different frame rates. Common materials for photon detectors, as we discussed previously, are INSB, SLS, MCT, and there's many more in the midwave region, and then MCT and SLS in the long wave. And since these sensors are able to detect emitted photons, they actually must be actively cooled to reduce the noise caused by self-emittance. This is the reason most photon detector-based cameras are referred to as cooled cameras, because they're being cooled down to 77 Kelvin or another temperature depending on the detector characteristics. This cooling is often done using a Stirling cycle cooler that cools the detector down. And to prevent condensation and frosting at such low temperatures, the detector is actually contained in a vacuum package that's mated to the cooler. The entire assembly that is created is often called an IDCA, or an integrated detector cooler assembly. Without this cooling, a photon detector camera would produce an incredibly noisy image. So the next question that naturally comes up whenever we talk about all of this is, well, when practically should I use a cooled or uncooled camera? And so below are the advantages and disadvantages of these two different detector types from an application perspective. Some of the main advantages of cameras using thermal detectors stem from the detectors being uncooled. Since the detectors don't require active cooling, the cameras draw less power, they're generally smaller, they can run off batteries to facilitate portability, and the lack of a mechanical cooler means they have longer mean times before failure, which makes them suited for 24/7 applications. Think SWaP-C, size, weight, power, and cost. However, as we detailed in previous slides, some of the limitations are the relatively long thermal time constants, reducing maximum frame rate. The rolling shutter type of readout processing also doesn't allow for discrete triggering of a single frame. And in general, they're less sensitive than cooled photon detectors due to their higher noise. So on the right, you'll see for the cooled photon detector-based cameras, their main benefits can be summed up with what we like to say the 5 S's, and that is sensitivity, speed, spatial resolution, synchronization, and spectral filtering. We'll have a quick overview of these in subsequent slides. And as for limitations, since the photon detectors need to be actively cooled, they draw a lot more power, which makes them generally larger and less portable. And since the mechanism for cooling is typically a Stirling engine, they require routine service and have lower mean time before failures on average. So we call these the 5 S's, and we're going to go over just a couple of them now to give you an idea and some practical examples. The first characteristic is sensitivity. And on this slide is the classic handprint demonstration. If you've ever been introduced to a thermal camera, you've probably seen this handprint demo from someone. For all its practicality, right, in any setting, it's very easy to do. It's actually exciting. Who knew that just briefly touching a wall could transfer so much heat? But this is where you step back and you remind yourself how little heat you actually transferred from your hand and actually how sensitive all of these cameras are. So in this demo, you'll see on the left-hand side time 0, okay? And we can see how a photon counter compares with the bolometer at the initial touch. You can see so much more detail on the photon counter image because each pixel can actually read smaller steps in temperature versus the noise, whereas the bolometer camera is experiencing a much harder time with its signal to noise. So over time, 2 minutes to be exact, if you look at the second column, you can still very clearly see the handprint with the cooled camera. However, the handprint on the bolometer image is almost at the point where you might not identify it as a handprint at all. And that's the challenge here. The handprint is beginning to reach a temperature value where the camera can no longer tell the difference between it and the noise floor. It's approaching the NEDT limit for the bolometer. So when working on applications where you need to be able to resolve very low energy events or even transient thermal events, the bolometer-based detectors are going to have a much harder time, or it might even be impossible. So let's take a look at this in action with a more realistic application. What does improved sensitivity of a cooled camera system really mean when it comes to electronics design and testing, and why does that matter? So here are images from two different cameras looking at the same populated printed circuit board, which is energized to provide thermal contrast. We tried to match the field of view and adjust the scaling to get these images aligned as close as possible. We actually even cropped the images slightly so they'd have the same aspect ratio. The image on the left was taken with a FLIR long-wave uncooled microbolometer camera with a 640 by 480 pixel resolution and an NEDT of less than 30 millikelvins. So the left-hand image is an uncooled image. The image on the right is from a cooled mid-wave INSB camera with a 640 by 512 resolution and an NEDT of less than 20 millikelvin. So on the right is your cooled camera image. You can see some slight differences between the two images, and you can make out a few more details in the cooled camera image on the right. But when we zoom in to the region around the integrated circuit, you can clearly see the difference in the images. The imagery from the cooled camera on the right shows greater detail. You can see some thermal variation on the integrated circuit, and you can even see the individual traces on the board. In comparison, the imagery from the uncooled camera on the left appears washed out with less detail and thermal contrast. From a data perspective, the cooled camera produces more detail with less noise, highlighting even the most subtle differences in temperature. So now the second S of the 5 S's is speed. And though it may sound like a straightforward camera parameter on the surface, the measurement results and data quality can actually be vastly different when using an uncooled microbolometer-based camera versus a camera with a cooled photon detector. And we'll show you some really nice examples of this. As we discussed earlier, microbolometers have long thermal time constants, which limits the ability to respond to thermal energy reaching the detector. These long thermal time constants also constrain the maximum frame rate, since the camera cannot output images faster than they're being generated. For cooled photon cameras, the collection and conversion of photons into electrons happens almost instantaneously, which allows a full image frame to be created quickly. In addition, the efficiency of this conversion process, referred to as quantum efficiency, allows the detectors to have low noise, usable signal much faster than a microbolometer. This allows cooled camera systems to run at shorter integration times and output higher frame rates. Cooled cameras also have the ability to change frame rates, window down the detector, and change integration times with these. But what does this actually look like in the real world? Let's see some imagery and some examples. Fast frame rates are a side benefit of short integration times, analogous to shutter speed, right? So this means that cooled cameras can image the same scene temperature as a bolometer camera just much faster. So this allows you to stop motion and avoid image blur on fast moving targets. The following images illustrate this by stopping motion on helicopter in flight and a fan blade, the top and bottom images. The bolometer cannot even stop the distant helicopter blades in the top left image, and instead you see the blurry carryover of the charge. But on the right, you can see the aero heating on the helicopter blades. It's really pretty impressive. And then on the bottom images, the bolometer can't even detect the fan blades due to these time constants. However, the cooled camera can see the fan blades clearly. See, bolometers, they're great for general purpose applications, but when it comes to speed, they just aren't designed for it. I want to take just a moment before I show any more imagery to remind everyone, if you have questions or have some comments and things like that, please submit them on the question portal. Ross is sitting there ready to respond, ready to interact, and continue to answer questions if you have them. So please go on there and submit them if you have any questions during the presentation. And then you're also willing to submit the questions afterwards also. So here's another example of thermal smear and blurring. Some of you may have seen this imagery before, but if not, it's actually a capture of a heated and dropped golf ball. And as in the other images here, we have a similar resolution cooled versus bolometer detector. Both of them are running at 60 hertz. And on the left, the bolometer image is clearly smearing due to the speed of the ball versus the speed of the camera. But on the right, you get a crisp image. But let's look at this in more detail because there's more to this. We said we actually collect data, just not videos, right? So if we take a closer look at the actual data, you can see how the smeared image doesn't even accurately reflect the surface of the ball. Here, we have the data displayed in FLIR Research Studio, with both data files playing on the left, with region of interest line profiles placed across each ball, the red and the green respectively. On the right, we have both of these line profiles displayed on a chart. The bolometer is green and the cooled camera is red. If we take a look at the green bolometer line, not only does it have a wide disparity of apparent temperature readings, but you can't even really tell where the ball begins or ends. With the cooled camera, the shape is clear, the data is great, and the imagery really is quite impressive. The golf ball like this is a really easy example, and we can actually see that the data being displayed by the microbolometer is wrong. This is easy to tell because we know what our object looks like. It's a golf ball. But in a lot of test scenarios, the shape or profile of the defect may not previously be known. With significant motion blur on a microbolometer, a decision could be made on incorrect data. This could prove to have negative consequences down the road if critical design parameters were made based on this incorrect data. Here are just a few more examples of where high speed achieves superior results. On this slide, you can see a tire spinning comparison. On the left with a cooled camera, you can clearly see the tire. And on the right with an uncooled camera, you have significant motion blurring on the rims. I'm moving through these a little bit quick. The last one here, this is one more example. It's a bottle seal inspection application. Here we're imaging a production line with bottle seals. At the top, you can see the motion blur from a microbolometer. To use an uncooled camera or a microbolometer here, you would have to slow down the production line, reducing the output. But on the bottom, you can see the same production line, you're running at the same speed using a cooled camera. In this image, you can actually see each individual seal. So let's go back to the 5S's: sensitivity, speed, spatial resolution, synchronization, and spectral filtering. It's very simple to remember, and that's what we like. And it really helps convey how cooled cameras have an advantage over uncooled cameras in providing meaningful thermal data that supports critical decisions. We went over sensitivity and speed today, but for the sake of time, we will not discuss the other three. You'll see a link in the chat for individual webinars presenting each of the 5S's in depth. If you would like more information on the 5S's in your specific application, you can also reach out to us after the webinar, and we'll provide contact details at the end so that we can connect you with our sales engineering team. So here at FLIR, and specifically in the research and development and science market, we have cooled and uncooled product offerings. You can see on the left the fixed uncooled offerings. The A700 series at the top is a larger motorized focus camera option that includes a visible camera and many more features. And then below, the A70, A50 is a smaller fixed mount and fixed focus camera family. Those are both microbolometers. This is just a summary. We actually have many more cameras in both of these portfolios. On the right, you'll see the main two families of cooled IR cameras, the A series and the X series. The A series are our commercial and university lab grade cooled research cameras. And then the X series cameras, they're incredibly flexible. They're our flagship research camera for the highest end applications, where a dropped frame just cannot happen, where spectral flexibility is needed with filter wheels and high speed and lots of different features that make it our flagship research camera for very high end labs and applications. We also have RS cameras, which are outdoor, longer range scientific cameras with very long continuous zoom lenses, producing data at every single focal point within the zoom range. So really unique part here, though, is that all of these cameras work in Research Studio and can stream multiple cameras at the same time to a single computer, as we'll show you in just a little bit. So before we spend a few slides on the theory behind calibrating an infrared camera, I'd like to talk about factory calibrations and the basic steps to perform a calibration and get temperature output. Essentially, I'd like to start with the broad overview first and the simple explanation, as the theory can get quite deep. If you look on this slide here, our cooled cameras, you can purchase, calibrations are typically purchased with every single new camera and with the uncooled cameras. They provide high quality nukes when you do a factory calibration, accuracy to plus or minus 2C or 2% for many cameras, and temperature drift compensation, which we'll talk about in a minute. You'll see listed some standard calibrations below. In summary, negative 20C up to close to 3000C, depending on the option selected. And factory calibrations are best for 99% of situations because we can provide high quality non-uniformity corrections. We can provide a high quality calibration with high quality black bodies. And then finally, temperature drift compensation too, which is performed as a part of our proprietary calibration process. So the quick overview of the 4 steps, and then we'll dig into the theory. The first step you'll see on the far left is to identify an appropriate integration time for the target scene. So this is effectively your camera's exposure time, as we talked about before. If you set it too long, you'll saturate, and if you set it too short, you won't fill the detector well adequately enough to get good imagery. It'll be noisy. And so depending on the temperature range that you're looking at, you would set this integration time. And we typically recommend setting the integration time to where the detector fills to roughly 80% at the top end of the temperature range. For a 14-bit detector, that's a little over 13,000 analog to digital counts. Then the next step is to perform a non-uniformity correction. It's performed to align each pixel utilizing gain and offset tables along with a bad pixel map. Essentially, this gives you a cleaned up and uniform image. Once you have this cleaned up and uniform image, and you have an integration time that's getting you the best imagery possible, then we capture specific temperature data points to build out a calibration table. This is where we relate digital counts to radians, and then ultimately to apparent temperature units. There are multiple points taken across the temperature range, which then build the curve for this conversion. Finally, the final step on the right is T-drift, or temperature drift compensation. We run the camera through varying ambient temperatures in a temp chamber to create automatic temperature drift compensation. This means that the camera is always taking ambient temperatures in and around the sensor, and then it'll correct for changes in the ambient that can affect the stability and accuracy of a measurement. So those are the basic steps behind a factory calibration. There's also a user calibration option that we have software for in Research Studio, where these basic steps apply. But the equipment to do calibrations with black bodies, area and cavity black bodies, can get quite expensive and take considerable time and expertise. And that's why for 99% of the applications, it makes sense to have factories calibrations done in the factory. As a part of that, I just wanted to show this image real quick. Here at FLIR, we calibrate more cooled and uncooled cameras than anyone in the world. And this is an example of what one of our calibration labs looks like. Here you see NIST traceable black bodies ranging from negative 20C to 3000C. This arm allows us to fully automate the process for efficiency, consistency, and quality. And the basic steps that we discussed get carried out in these calibration labs, which FLIR has multiple throughout the world. As you can see from the equipment here in this image, and this isn't even all the equipment required for a calibration, that it can get quite expensive and can take significant technical expertise to get a good calibration. Essentially, anyone can return a number per pixel in a camera, but to know that that number actually represents a temperature value that is accurate across varying ambient conditions is extremely difficult to do. Okay, now we had the quick overview of the process from a simple perspective. We're going to dig into the theory just for a couple slides, okay? And so imaging radiometry is detecting and measuring radiant energy from the scene using a calibration that maps pixel signals to scene brightness, and then ultimately to temperature or some type of engineering units. The radiant energy can be reflected, transmitted through an object, or directly emitted by the object. Good radiometric cameras will correct for systematic effects like lens temperature also. So while many IR cameras that you see on the market are only used for video to provide visual awareness and support basic decision making, think about a general security camera or detecting water intrusion in a building wall. Researchers interested in leveraging an infrared detector or camera for scientific and research applications, or even more advanced automation applications, need a camera that produces a consistent and reliable unit of measure. So in this section, we'll talk about a couple common units of measure: radiance, radiant intensity, and apparent temperature, and we'll see how we get from a photon to a useful measurement. So we need to level set in terms of units of measure for just a minute. Common units of measure, like we mentioned before, are going to be radiance, radiant intensity, and apparent temperature. And in order to get radiant intensity or temperature, you first have to calculate the radiance. And before we dive into those three units in red, the final units, I need to explain a couple terms and a couple of our source units. So the first term is actually the steradian. The steradian is a unit of solid angle. And if you're familiar with plane angles or radians, like you see in the image on the bottom left, then you can consider that we're talking about taking that planar angle and applying it to a three-dimensional space. This produces a conical shape, where we're measuring the area on the sphere versus the length of the circle. If you're having trouble with this concept as it applies to an IR scene or to a camera, think of the area on the sphere as the bigness of a light source as seen by the receiver. So in the real world, if you've ever had a flashlight pointed at you, you know firsthand how the light source differs from the source of the flashlight to how it feels at your eye in terms of area or size. Okay, so let's jump down to the units of measure. To get to radiance, we need an understanding of radiant energy. Radiant energy, the very top unit towards the top of the slide you'll see, is the total energy being emitted by an object. This is measured in joules. And then radiant power, on the next row, is also called flux. This is the measurement of the rate of the energy flow from the object, measured in joules per second. It is the rate of the flow of photons over a period of time. Radiant energy is joules, and radiant power is joules per second in summary. And so then joules per second is actually watts. So now that we have these, neither radiant energy nor radiant power are directional values, right? And so this is where the solid angle, or the steradian, comes into play. So we have all of our units of measure now, so let's look at radiance. Radiance is actually how bright something appears. It's the base unit of radiometry, and it's measured in power units as watts per square centimeter per steradian. Radiance characterizes how radiant IR energy per unit area of an emitter flows out of an object into space in a particular direction. Radiant intensity, the next unit, is the measure of radiometric power per unit solid angle, and as such is calculated as watts per steradian. While they sound similar, you should note that radiance is a value of the flux coming from a unit emitting area being the key word, whereas the emitting area doesn't matter for radiant intensity because it's for point sources. In fact, the radiance can actually be considered as radiant intensity per unit emitting area. Finally, this is the one that most people end up seeing and caring about, is apparent temperature. It's the easiest term to understand, and apparent temperature is typically expressed in Celsius or Kelvin, and it's based on the radiance. Once you have a radiance calibration, you can usually also determine the apparent surface temperatures for many types of targets. So, how do you get from radiance to temperature? This is our final slide on the theory here. Our software will perform this for you, but we like to provide an understanding for you of the relationship and how it applies to logic behind other key aspects of radiometry and thermography. So, Planck's law shows us that for a given temperature, a specific amount of radiation is emitted, and that the amount of radiation emitted is unique to specific wavebands. You'll see that on the left. On the left, Planck's curves are drawn for specific temperatures. Note how as the temperature and radiation emitted climbs, the peak of the curve slides to the left to shorter and shorter wavelengths. An easy way that I like to think about this is by considering a piece of hot iron. Once the piece of hot iron is hot enough, the radiation emitted actually becomes visible. The iron turns red hot because for that temperature, the curve has slid so far to the left that it's now in the visible spectrum wavebands. This means that overall, hotter black bodies radiate more brightly, but also with progressively shorter wavelengths. So in order to get temperature from radiance, you simply inverse the Planck's function. So now let's look at the chart on the right. Radiance versus temperature is shown. One interesting aspect to note here, though, is how different the radiance to temperature curves are between the midwave and long-wave bands. If you compare this to the Planck curves, you can see that there's a much more drastic slope in the midwave wavelengths, whereas in the long wave, the Planck curves begin flattening out. Since there isn't as much power change in the long wave, you can cover a wider temperature range with a given integration time versus the midwave. You can also go to higher temperatures before needing to apply a neutral density filter to maintain a reasonable integration time. So here's some key points to consider when you're looking at the differences. In the midwave, there's more thermal contrast, and there's certain phenomena can only be seen in this band. It also sees farther through humid air, and it's less expensive cameras and lenses than in cooled long-wave SLS. It also has higher QE relative to typical long-wave SLS detectors. Advantages to SLS are shorter integration times for same calibration temperature ranges. There's certain phenomena that can only be seen in long wave. There's higher dynamic ranges, better images for cold scenes, and then as we mentioned before, less stray light in high contrast scenes. So in summary, modern infrared detectors, they're highly sensitive and they're very flexible. With the right tools and familiarity, a researcher can optimize their camera for a very unique capture. In terms of where you should operate in the spectrum, in the broad sense, there's no better waveband to use. The application drives the requirement every single time. Regardless of the application, FLIR has cameras and advanced software to help scientists and engineers address nearly every single one of these applications. So please reach out and contact us. Our sales engineers would love to discuss the differences in wavebands, the differences in the detector technologies, and how it affects your particular experience. So our final topic for the day, and I'll move quickly through this because I'd like to leave a couple of minutes for questions at the end, but this is FLIR Research Studio, and it might be our lightest and most fun topic, less physics, less units, and more about how the software can make you successful. Ultimately, for any R&D professional, the camera or the sensor is important, right? But the user is mostly going to interact with the software to control the camera, to record, to do analysis, and to share with colleagues later. And so the software is actually where the user spends most of their time. With that in mind, we've aimed to transform the user experience of high-end research software. We have a vision to be the easiest to use, the most flexible, and the most customer-driven research and development software. Research Studio has become an industry standard and the tool of choice for many R&D professionals around the world. And I want to share with you quickly why. Some of the core pillars of Research Studio are multi-operating system. We know that many companies and research groups operate in Linux. They also operate with Macs, and they operate in Windows. The flexibility to use any of those systems at any point in the research process is a huge value driver. Multi-language, with teams distributed around the globe for companies these days, it's very important to be able to localize. And so the multi-language aspect of Research Studio lets these teams work in a language where they are comfortable, but it also lets them collaborate with global colleagues across a project. The third piece here is a simple workflow. We think of everything in Research Studio in terms of 5 buckets, and that's connecting to the camera, viewing data, recording data, analyzing the data, and then sharing the data with colleagues later, either to management or sharing for analysis. Finally, the ability to stream multiple cameras at the same time is very powerful. You can stream multiple cameras or load in multiple data sets at the same time. This lets you as a researcher acquire data with as many cameras as you need on the test with varying levels of functionality, varying spectral bands, speeds, resolutions, fields of view, whatever is needed. And it all can be acquired from one software platform and one computer at the same time. And the limitation here is not on the software, it's on the computer hardware. You can stream and you can record as many cameras as you want based on the hardware capabilities. Another huge value driver of Research Studio is this unmatched camera portfolio. Being FLIR and being Teledyne gives us access to vast technologies. And this isn't even all of them on this slide here, but you can see a researcher can start to learn about infrared in a university lab setting, right? And use uncooled microbolometers, and then start to purchase more cameras in their lab, even cooled cameras, but still have the same software platform that they know and love, that they already have trained their team on, and be able to use this for all of the cameras at the same time, but also reducing startup time because the team already knows how to use it. You'll see here the uncooled and the cooled. This vast portfolio in one software platform is a huge value driver for many companies and labs. I mentioned these 5 buckets or 5 steps. We know that when you're using our software, you may start at a different stage depending on what you're doing, but these are the 5 steps that we see: connecting and controlling cameras, viewing live data and optimizing it, recording the data with unique requirements and without dropping frames, analyzing the data later or exporting it for analysis, and then finally the ability to share the data with colleagues. Some very unique things about Research Studio that I'll mention real fast is we understand the importance of recording data. Tests are extremely expensive, and to lose a frame at the most important time could be devastating to a researcher or to an experiment or to a program, right? And so we provide lots of tools in Research Studio and on our cameras to help you know the status of your recording, to help you know the status before the recording, and to set up recordings to get the data exactly when you need. And this is performed a lot of times in our recording info dashboard. Another really unique part about Research Studio that I'll highlight, and then we'll move on to take some questions, is that we don't treat Research Studio as a software that we developed and we released it and we're done. We actually treat this as a continuous approach where we're always getting feedback from our customers, from researchers around the world, and we provide updates throughout the year to the software. Not just bug fixes, but user improvement updates and significant feature sets that can change the way that you can research. And so Research Studio is always evolving, it is always growing, and this slide shows that quite well if you look at the amount of releases and the amount of features and bug fixes that were released in 2024, and we're continuing that this year. And to further iterate that, just in January, we released a new version of Research Studio allowing for multi-window. When we allow people to connect with multiple cameras and multiple data sets, the ability to see more things at the same time is very important, and everyone has multiple monitors today. So this lets you use as many monitors as you want with Research Studio to give you more screen space and analysis area. Full screen mode is really important, especially for viewing a test, maybe with management watching. Camera controller docking lets you optimize your camera while seeing the imagery at the same time, and then various hotkeys just to make your operation faster as you become a Research Studio expert. So that's all we have in the presentation today. I'd like you just to refer to some links that are in the chat for a free guidebook, but also for information on FLIR Research Studio. We have a free 30-day trial, and we'd love to connect with you. Let our team walk you through just some basics on how to use the software and maybe how it can make you successful in your research.
Thank you, Matthew, for presenting. We now have time for a few questions before we wrap up. If you haven't already, please type your questions and comments into the webinar chat. Ross will be now taking over.
Hello, everybody. I was trying to answer these as they came in. One of the first questions was about minimum system requirements. So the minimum system requirements are documented in the FLIR Research Studio manual. When you install FLIR Research Studio, it installs the manual along beside it. Anyone can download the software from our website, just from the main product page, and it will run fully featured for 30 days, and the manual's right there. The minimum system requirements are quite generous. It doesn't require much. That said, don't buy a super high performance, very expensive FLIR camera and find an old computer in a storage shed somewhere and try to use that. It just won't be a great experience, and you'd be shocked by how many customers do that sort of thing. So I would buy, a nice i5 or i7 processor with 16 gig of RAM or more. You typically want a really nice display because the image is important to us here. But the minimum system requirements are not that difficult. A number of questions came in regarding how we can deal with emissivity. So our software, let's just call it FRS for short because we're going to be saying it a lot, has a built-in emissivity calculator. So if you happen to know the temperature of your test article, you can tell the software, maybe the software goes, I think this is 48 C. And you say, nope, I know this is 60 degrees C. The software will calculate what the emissivity must have been for that to be true. And you can know this by applying a known coating to your part and measuring the coated area and knowing that the adjacent area should be about the same. Or you could use cavity effects if there's a hole or a crease in your part where you know the emissivity is good there. Or you could put your part in a small oven, even a toaster oven, and heat it up uniformly to some known temperature, pull it out really quickly and make a measurement. Another question was, can we deal with emissivity that varies with temperature? We don't have a good way of doing that at the moment, but if your emissivity changed significantly through the course of your test, you could break the data file into separate sections using a piecewise linear approach and specify the emissivity for each of those sections using the tool I described previously. And we do have a video that shows how the emissivity demo works that we can probably get out to everyone who attended. Lots of people were asking if you'll get a recording of the webinar at the end. Yes, we are going to do that. It'll take us a little bit to get that uploaded. Others wanted, we covered 2 of the 5 S's, and others wanted more information there. If you'll just reach out at the end of the webinar with your location and let us know that you're interested in more, we can have your local FLIR Science Camera sales engineer reach out to you and provide, we have a presentation on the 5 S's, or they could learn about your application and give you specific guidance that may be helpful, or even stop by if you're here in the US. We do direct sales, and we're happy to come out to your site and do an on-site demo. Okay, would I be able to pick multiple points on the screenshot to create multiple data streams for analysis and graphing? Absolutely. So you can place as many regions of interest on the image as you would like, and for each region of interest, you can plot the minimum, maximum, or mean temperature. Furthermore, you can set up your workspace exactly the way you want with all of the analysis and save the workspace such that later on you just open that workspace and it brings up the data file and all of the analysis that you've done. Even better, you can save the data file as a FLIR Research Studio player file, and this will allow you to give a copy of the data and that workspace to a customer or a colleague. They can open it on their computer using the free FLIR Research Studio player and see the exact screen and analysis that you were looking at, so they don't have to rebuild it all from scratch. That's an incredibly powerful feature of FRS that was not available in prior FLIR R&D software packages.
One other thing to mention too, Ross, with that is you have the ability to build custom functions. We call them measurement functions. And so you can take regions of interest and statistics or really any type of data from the camera or recorded file and combine it with a function from other files and then plot and do various things with it too.
Absolutely. You'll find that FLIR Research Studio can probably handle most of the analysis that you want to do. But if you're doing something beyond the capabilities of it, something super specific, we also have a FLIR file SDK that will allow you to natively open our file format from any C-based programming language or Python or MATLAB. A question came in regarding camera calibration. So there are 2 types of camera calibration. There are factory cals and user cals. The factory cals are going to come with a 1-year sticker, and we have to do this according to NIST rules. The camera will generally be accurate longer than that, but we can guarantee that 1 year. And then you can send it back to us, and if you want, we can give you an as received and as left calibration on the recal, so you can make sure that it was still in cal when we received it and see what the new data is when we shipped it back out to you. If you're doing your user calibration, then by definition, you have all the hardware on site to verify if the camera is still accurate or not, so you can decide what your validity is on that. Okay, there's some questions. Some people have Research IR, which is our previous generation software, and they were just asking about the differences between the two. Research IR was fantastic software, industry leading for many, many years. But with FLIR Research Studio, we have the multi-OS capabilities, so you can run it on Windows, Linux, or Mac. We have a much better way of sharing data now with the FLIR Research Studio player file. Previously, we used something called a self-viewing file, and it was groundbreaking at the time, but it was an EXE that was limited to 2 gig in file size. That's not the case anymore with the player file. And we can open multiple camera feeds or cameras and data files in the same instance of the software, which is a huge deal. And then also our latest generation of X series cameras have features on there that aren't supported in the old Research IR regarding saving directly to the camera and offloading from the camera down gigabit Ethernet back to the computer. So if you're using the latest generation of X series cameras, you want to make sure to use FLIR Research Studio. Matt, do you have any more to add on that one?
I would just say in general too, Research IR is no longer being updated. So as
Yeah.
Windows has changes and things like that, you really need to be on the new software, even from just a like patching standpoint and working with future cameras. There's really no functionality in Research IR that Research Studio does not have. And then of course, we mentioned a lot of them rusted, and you saw them on my slides. Uh, Research Studio will really change the game for you. Every customer that we've transitioned over the past couple years to Research Studio has been very happy that they did.
Question came in, does your microbolometer measure at two different wavelengths and then use ratios? This is a common, to get emissivity, this is a common approach used by spot pyrometers. So just little temperature measurement guns that typically shines a laser out to show you where you're pointing, and supposedly they correct for emissivity by being two color. Our microbolometers don't work like that. They measure all of the energy in something like a 7.5 to 14 micron wave band, and they have no way of sorting out emissivity on their own. So as the user, that's your responsibility to make sure you have a good emissivity and reflected temperature entered. There are lots of questions about emissivity, so that tells us that maybe a future webinar should be emissivity centric,
Yeah.
and we'll send some information out in the package that everyone gets on this, showing how the emissivity calculator works.
So Ross, I think that may be all that we have time for in terms of questions. So if there's any we were not able to answer, we'll follow up afterwards on those questions.
Yeah, kind of like Matthew said, if we haven't answered your questions yet, please look out for a reply from us via email later. If you think of another question, feel free to email us at webinar@photonics.com. I'd like to thank our presenter one last time, Matthew Hastie, and thank you all for participating in the Introduction to Imaging, Radiometry and FLIR Research Studio. This event was presented by Teledyne FLIR and hosted by Photonics Media. Thank you all so much.
Thanks, everyone.